Welcome to this segment on electrochemistry. Today we'll be talking about redox. Redox is a made-up word made up of the words reduction and oxidation. A reduction is a gain of electrons, and oxidation is a loss of electrons. And we have this little word here, Leo-Ger, which can help you remember. If you think of Leo the lion says Ger, that'll help you remember that loss of electrons is an oxidation, the gain of electrons is a reduction. But before we get into this a little bit more, I always think of redox as a matter of perspective. Let me tell you what I mean. Here is every Canadian's sort of worst nightmare, the rusted car. We live in a cold climate, cars rust, and we got to spend money to replace them. So here's some rusty cars. This poor little fella, completely rusted out. Here, not so good. Over here, just driving down the road, getting ready to be pulled over by the cops at any point in time and taken off the road. All examples of rust. So here's the reaction where rust is formed. Okay, this is iron, but car bodies are largely made of. Reacts with the oxygen in the air. Of course, moisture and salts on the road help as a catalyst. And you end up with rust. If you take a look at this equation in a little bit more detail, we can see that on this side we've got iron, okay, neutral iron, iron metal, and within this iron oxide, it's actually iron 3 oxide, the iron has become Fe3+. And here's oxygen, okay, oxygen the way it's in our atmosphere, and within iron 3 oxide it has become an oxygen ion. And so the top reaction that's being shown here is an oxidation, because iron goes from being neutral to having lost 3 electrons. Loss of electrons and oxidation. And this other one then is a reduction. Oxygen has gone from being neutral to gaining 2 electrons. Gain of electrons is a reduction. So my main point here is that when we think of cars rusting, there's actually an oxidation taking place and a reduction, but we take the view of the metal because the metal costs us money and we care about the metal. And so we call this an oxidation. We say, oh look, an oxidation has taken place. Where in reality, there's an oxidation and a reduction taking place. If you consider for a sec, I want to give you another example. Consider the unfortunate situation where a person gets hit by a car. Okay? A car accident takes place and people will say, oh no, that poor person, that poor pedestrian, he got hit by a car. We seldom take the view from the other direction and say, oh my goodness, this poor car was driving by the road, down the road, and suddenly a person hit it. Technically, it wouldn't be inaccurate, but we take it from the perspective of the pedestrian getting hit by a car, not the other way around. Same thing here. This example is an oxidation and a reduction. It's a redox, but we always take the view of the metal, in this case the iron. You can say we're biased that way. And so here, there's a bunch of examples, and it says they're classified as reductions. Why? Well, because in each case, the metal is being reduced. Okay, here there's a metal, positive, which has a positive charge, and it becomes solid iron, which is neutral. Here there's tin, here there's copper. In each case, the metal is getting reduced. And so really, if the metal is getting reduced, some other compound or element must be getting oxidized, but again, we're biased from the perspective of the metal. Over here, same idea, there's a bunch of oxidations. Here's copper getting oxidized by bromine. Here's magnesium getting oxidized by oxygen. So you'll notice it doesn't always have to be oxygen that is doing the oxidation. And again, it's from the perspective of the metal. Okay, and so we can write half reactions. Here is the half reaction showing the reduction of silver. And there must be something getting oxidized. There must be some kind of oxidation taking place, whether or not it's shown or not. And over here, we see copper getting oxidized. And again, this can't magically happen on its own. There has to be some sort of a reduction taking place as well. And last of all, what I want to mention is that you'll notice if you start thinking about this and looking at lots of equations, chemical equations that you've seen before, you might ask yourself, what's not a redox reaction? Because you'll notice there's a lot of reactions that could be classified as redox reactions. Okay, you can take a look at a combustion reaction and see whether or not that could be a redox reaction. But one thing you'll notice if you do this is that double displacement reactions are not redox reactions. So the next thing then is to look at electron bookkeeping. And by that I mean look at oxidation numbers. So here's a chart which is available in the Nelson textbook on page 658. And yes, you can memorize this chart, but if you practice a little bit with the chart in front of you, I think you'll become quite quickly comfortable with just knowing what the oxidation numbers are without having to refer to a chart. One thing worth stating, as a convention, when we write oxidation numbers, let's write +2 instead of 2+. 2+ looks like a formal charge on an ion, and so we'll use +2 to indicate oxidation numbers. So let's start by doing some examples. Here we've got water, so let's figure out the oxidation numbers. We've got oxygen. According to our chart, oxygen is almost always -2. The only exception to that is peroxides. H2O2 is hydrogen peroxide. And unless you see that, almost always oxygen is -2. So we write -2, the oxidation for the oxygen. And hydrogen then, okay, hydrogen is almost always +1. And in this case, if hydrogen is +1, well, 1 times 2 is +2, because there's 2 hydrogens. And so overall, this compound is neutral, which of course it is. So then we figured out the oxidation numbers of the elements in water. Next, let's take a look at the nitrate ion. So in nitrate, again, oxygen is not a peroxide, so it's going to be -2. And now we've got to figure out nitrogen. Well, if oxygen is -2, there's 2 of them. So altogether, it is 6-. So now we have to do a little bit of algebra to figure out the oxidation number of nitrogen. Well, we'll call nitrogen X, its oxidation number. And so X minus 6, the charge of nitrogen, plus the charges of all the oxygens, have to equal -1, because this is a nitrate ion which has a formal charge of -1. And so of course if you do this algebra, you add 6 to both sides, and you see that nitrogen ends up having an oxidation number of +5. The next example. The next example is just an element, okay? Atoms and elements, don't get tricked by this, as people often do, always have to be neutral, okay? So over here, hydrogen has to have an oxidation number of 0. The next example, acetic acid. Well, oxygen is not a peroxide, so it's going to be -2. Hydrogen generally is +1, okay? If it's in a hydride, hydrides are relatively less common situations where the hydrogen is a -1 ion rather than a +1 ion. But that's not in this situation. This is just acetic acid. And so hydrogen is +1. And it's also going to be +1 over here. You know that acids form +1 ions. And so we just need to figure out carbon. And so if we remember again that the acetic acid molecule has to be neutral, as all molecules are, then whatever the charge, the oxidation number on the carbon is, and there's actually two of them, not that it changes the equation, 2 times that charge plus all the positive charge, and there is 3 hydrogens, plus all the negative charge, and there is 2 oxygens, which each have an oxidation of -2. So 4 hydrogens altogether make +4, the 2 oxygens make -4, and this 2x, all of this has to add up to 0 because this is a neutral compound, unlike the nitrate ion, which is not neutral. And so we do a little bit of algebra, and we arrive at 2x equals 0, so x is equal to 0, and so that is the oxidation number of carbon. The next one then, KMnO4, oxygen, not peroxide, so it's going to be -2. Potassium ion, K+ ion, it's a monoatomic ion, and so it's just the oxidation number is whatever the charge on the ion is. And with potassium, you probably know that it's +1. And so we do again a little bit of algebra here. Manganese is X, and so X plus 1 minus 2 times 4 is equal to 0. And so X plus 1 minus 8 is equal to 0. So X minus 7 is equal to 0. So X has to be +7. So manganese in this case is +7. So here's a couple more examples to try on your own. And in the next lesson, we'll begin by taking a look at this example over here, because the oxidation number here of iron is strange. It's strange in that it's not a whole number, and in fact it's a fraction. So when you try the other examples, consider that this one is going to give you what perhaps looks as a strange answer initially.